Thank you for the kind introduction, and it's such a pleasure to be here today. It's also really fun to kick off this event. It gave me an opportunity to think about ways to tie together so much of our work across both the U.S. and Israel in really advancing the security, affordability, and sustainability of water supplies. These three objectives, security, affordability, and sustainability, have really defined both the academic community's research endeavors in the water space, but also our nation's infrastructure investments in water. When you think about early work, for instance, in the development of seawater desalination membranes and the translation, all the way through to the construction of very large desalination plants, this agenda has really helped to catalyze and really set the playbook for how nations can respond to water stress and water security and ensure that there's adequate water supplies for human health and economic prosperity. And yet I think it's also important to be frank while celebrating these successes about the challenges ahead. As Avner mentioned, I'm particularly concerned about challenges insofar as they interface with our energy and climate systems. And in particular, I think we are looking at a future in which we're not just going to see greatly expanded water stress, especially in places away from the coast, in the case of the US. But we're also entering an era in which we're going to see a great deal of additional climate variability. And that climate variability, I think, is going to stress water systems and challenge the traditional solutions that we've had in addressing security, affordability, and sustainability of those systems. As I mentioned, in the US, we're actually seeing a lot of expanded water stress in the interior of our country, requiring that we tap different non-traditional water supplies. We're also seeing a lot of additional volatility. So this is some recent work from the state of California looking at how water resource availability or precipitation is going to increase its volatility over time. And I'll just say that I think, it's okay to fall back on the traditional playbook of increasing efficiency, adding storage in the system, building conveyance, and tapping those non-traditional water supplies when we're in an era of sort of low volatility or moderate volatility. But we've invested a lot in infrastructure systems that are not exactly prepared to move into a direction of high volatility. So in a low volatility regime, you have both economic feasibility and political palatability because your desal plant is operating all the time, right? People see it working, it's being used. In an era of higher volatility, that infrastructure suddenly has to address a 90% supply deficit in 1 year and turn around and manage massive flooding in the next. And that's much, much more challenging to design for. It's also much more costly to design for. And so this, I think, sets us up in a little bit of a conundrum. We can either build a lot more of the same infrastructure, or we can build a very different type of infrastructure system or infrastructure network to natively adapt to that volatility. That's the challenge, first and foremost, for securing water systems in an affordable and sustainable way under new climate regimes. And I want to talk in this presentation a little bit more about how I think we can help get us there. So how do we maximize the financial value of investments and their adaptive capacity? I believe that doing so is going to require pretty substantial innovation in a couple of areas. We need infrastructure systems that are versatile, so they're doing more than one thing at the same time. We need distributed infrastructure that augments the capacity of central supply. We need infrastructure that's inclusive and finds ways to engage all sectors of the populace. And fundamentally, we're going to rely on much more adaptive control through digitization and integration of physical infrastructure and digital infrastructure to make sure this all works smoothly. So I want to share a little bit more about each of these elements and then spend most of the rest of my talk talking about a future of digitization in the water infrastructure space and ways that we as a research community can use digitization and ways that the practitioner community can leverage digitization. Okay, so let's start out with versatility. We need to make infrastructure multifunctional and unlock its value by creating infrastructure that can be repurposed on demand. This is true both of how we design and implement a water infrastructure. So you can think about the billions of dollars of investment that are going into upgrading US wastewater treatment plants, all of which were built 50 to 60 years ago, are ripe for reinvestment, and really demand at this point that we look for ways in which that wastewater infrastructure investment can serve multiple functions. How do we prepare wastewater treatment plants for reuse, even if they're not ready right now? How do we prepare them for a low-carbon fertilizer production, where we can really realize synergies with nutrient pathways? How do we use them for population health monitoring? So that's an example of how we can think differently about investing in the water infrastructure system to support water security. But I think we also need to look very critically at how we spend infrastructure dollars in other sectors and how that spending can also augment the security of water supplies. So for instance, I have colleagues that have done a lot of work on streetscapes. How do we, when we're investing dollars in building streets, also think about using them for flood control, for stormwater treatment, and ultimately for groundwater recharge? Or in the case of flood protection, where we're going to see a lot of investment over the coming decades, how do we think about using those dollars to also enhance natural ecosystems, fishery productivity, and water quality that might be also the source of our seawater intake for a desal plant? In addition to being versatile, versatility works really well for centralized infrastructure. I think it's really important to think about augmenting centralized infrastructure with distributed water infrastructure. So figuring out ways to help adaptively augment, particularly aging infrastructure or inadequate centralized systems with small-scale distributed systems in an adaptive manner. This has been a core mission space for the National Alliance for Water Innovation, which I serve as the research director for, and so many of you on the US side have so deeply contributed to. I think it's also been a real focus for helping cities like San Francisco. This is a picture of me taking one of my classes to the rooftop deck of Epic Cleantech. Epic Cleantech is a small company that builds and maintains and operates on-site water reuse systems for large buildings in San Francisco, buildings over 100,000 square feet that are required to have on-site reuse. And what you see in this picture are actually 3 different buildings. The tall one on the left, the one that's under construction in the middle, and then where the crane is the foundation of a 3rd building, all of which will have these small-scale on-site reuse systems. And those systems are, I think, particularly valuable, again, for thinking about ways that we can flexibly respond to dramatic variation in supply, but they're also helpful on a number of other levels. These large infrastructure systems, or I should say these large cities that are increasingly densifying in the US have real constraints in how large the conveyance system is. And rather than upgrade the entire conveyance system, we're seeing lots of value in minimizing the need for those upgrades through on-site reuse. We're also seeing lots of value in industrial applications where we can use the higher concentrations of contaminants in water and capture those at the source where it's easier to remove them, but also promote fit-for-purpose reuse on site at industrial facilities and help make sure that the industry is adequately supplied with water and not drawing down natural resources. Finally, I think we would all agree that there's tremendous additional value, in fact, some of the highest value when we see small-scale systems installed in low-density communities or in peri-urban areas where the kind of amount of infrastructure that we need to install is not well aligned with the financial resources that are available. And so that leads me to the next kind of key feature I see in infrastructure investments, namely that we need to really realize, or one of the places that we can realize the greatest value of kind of alternative distributed systems or small-scale systems is in places that we've historically had underinvestment in our infrastructure systems. They have the kind of furthest to go in terms of improvement. And a good example is a pilot project that NAUI has funded that's led by University of California, Berkeley, and operating in a small town of Allensworth, which is a town of 600 people in the Central Valley of California. They lack access to reliable, clean water supplies, and they don't have the financial resources as a town of 600 to build tens of miles of conveyance infrastructure to tap that water and bring it to their community. Instead, we're piloting a small-scale groundwater treatment system for arsenic removal to help ensure that there's reliable and safe water supply for that community. But I think it goes beyond just kind of thinking about new technologies when engaging these communities. It's also about new financial models for helping to finance and maintain small-scale systems, and about new modes of operation and maintenance, especially bundling the operation and maintenance of those systems to help ensure the sustainable operation over decades that these systems will need to serve their communities. I want to end this kind of attribute tour by sharing with you where I see opportunities in digitization, namely, how do we integrate digital and physical systems to sense, analyze, control, and adapt these significantly more complex infrastructure systems in real time. I think doing so is a fundamental challenge. We are asking these much more complicated systems to function efficiently over 12 orders of magnitude in time scale. And I think we would all recognize that doing so heuristically, relying on human expertise and experience, is functionally impossible, right? The systems themselves are becoming more complex, and so operating them is going to require the support of digital tools or computational tools to help aid and guide their coordination and their operation. This is, I think, been certainly a ripe area of research over the past several decades, especially thinking about how we can use control systems for treatment operations. But there's been substantially less thinking and execution of using those same control systems to help serve the integration of water systems with other infrastructure systems, or the coordination, particularly of water and energy systems, and the use of control systems when it comes to water supply portfolio optimization. And so today I'm actually going to talk a little bit more about digitization and focus the remainder of my efforts there. Zahi, I think, is going to share some additional thoughts and experience that he's had in automation and digitization of treatment system operations tomorrow afternoon. So the two other areas, this coordination with energy infrastructure and the ability to think much more broadly about the use of control in deciding what infrastructure to build, is, I think, a really exciting area. And I'm going to start sharing some of our group's work in that area. I'm then going to turn to where I see foundational research gaps in the development of digital twins for control and adaptive management. And then I want to turn to sort of serving not just the practitioner community, but how can we as a research community use digital twins to help inform what we decide to work on, where we decide to focus our fundamental research efforts. Okay, so I'm actually going to give this talk in terms of what not to do rather than what to do. So this is a picture of the Santa Barbara Charles E. Meyer desalination plant. I've done a lot of work with Santa Barbara over the past decade. And this is not by any way an effort to criticize Santa Barbara or IDE, which was the builder of this plant. But it is a critique of how we've gone about historic planning around expansion of our water treatment infrastructure. So in 1985 to 1987, there was a very, very severe drought in Southern California and coastal California. We were absolutely going to run out of water in Santa Barbara, and the decision was made to build a water desalination plant. It's a 3 MGD plant. It provides about 3,000 acre-feet per year, or 30% of Santa Barbara's water supply. It was constructed and commissioned, and it started up in 1992 just as historic flooding hit Southern California, and we saw massive and rapid filling of our reservoir systems. And so after 3 months of operation, the plant shut down and did not reopen for another 20 years. In fact, the whole plant was decommissioned, sold off in parts and pieces. And the effect was that the residents of Santa Barbara paid about $104 per gallon for the water they consumed over that 3-month period. Okay, so it's not to say that there wasn't retrofit. There was decommissioning of that plant. But I do think that there is a tremendous opportunity to rethink how we decide when to build new infrastructure and what new infrastructure we decide to build. Fundamentally, this more linear approach that you see on the left-hand side inspires us to build large capacity systems to buffer against hydrologic uncertainty. And that is kind of necessary if we're only revisiting our infrastructure decisions on a decadal basis. If we instead move to a more closed-loop water resource management system where we are revisiting the decisions behind our infrastructure construction on a much, much more regular basis, I think that opens up the opportunity to really leverage some more of the dynamic attributes of small-scale distributed systems. So I want to talk a little bit more about some of the work that our group has done in deriving optimal decision policies for when, where, and how to build out infrastructure. And we've done that, and we've looked at these technology deployment policies, again, in the city of Santa Barbara, using an algorithm, a tree-based reinforcement learning approach, to derive optimal decision policies based on historic drought characteristics. So the frequency, intensity, and duration of historic drought. We train models on tens of thousands of simulations of that historic drought. And then we use that to understand what technology or what are the decision policies that inform what technology to implement, at what volumes, in response to what triggers, and when you should decommission that infrastructure. So what you see is that Actually, for historic drought scenarios, it may very well have made sense to build centralized capacity and decommission it for a period of time. The cost optimal set of policies around infrastructure build out would have also made much more extensive use of decentralized infrastructure, so smaller scale infrastructure that could be commissioned and decommissioned rapidly without trying to recover a lot of the capital expense that you see in building a large centralized plant. And the other thing that you see here is that in terms of triggers, we have not just what's happening in the kind of historic drought space, but you're really using an understanding of storage throughout the system, your reservoir capacity, to inform or trigger when to build that infrastructure. So you see massive, you tend to build that decentralized capacity when you're getting big drops in how much storage you have in your reservoir systems. Because this is a digital representation of Santa Barbara's water supply system and hydrologic system, we can then perturb that to ask questions about what would happen under future climate scenarios where we might see significant changes in drought characteristics. So we can look at longer, more mild droughts, or shorter and more intense droughts, or more frequent droughts, and understand and update decision policies to reflect the different set of technologies or I should say, we update those decision policies to reflect the different hydrologic scenarios, which then inform which types of technologies get implemented. All of that also lets us look at what are the differences of cost between different future climate scenarios, which helps us place a value on understanding, measuring, and monitoring what exactly is happening in both the historic record and drought and how climate change is expected to change those drought characteristics. Okay, so I'm just going to conclude here and say that adaptive deployment is really important for minimizing costs within the scenarios, and the value of information that we get from looking at the effect of those different drought scenarios helps us as a scientific community to direct our research efforts toward really better understanding how future climate scenarios are going to change or preference one drought type over another. Okay, so the second example I'm going to give on the kind of digitization front is also one at the Santa Barbara desalination facility. When this facility was recommissioned in the early 2000s, it was built in a model and designed in a regime in which electricity prices in California were actually fairly flat. There was not, we were constrained, but not tremendously constrained in our generation and transmission infrastructure. And there was no time of use pricing at that period of time, which is to say that it wasn't more expensive to consume electricity from 4 to 9 p.m. than it was to consume electricity at any other part of the day. But over time, over the past 20 years, we've seen massive changes in our energy infrastructure, and I'm happy to keep going, but it's better to do so with slides, which is to say that this desalination plant today, which again has a baseline operation of 3 MGD, pays about $400,000 a month for electricity in Santa Barbara during the summer, and about $275,000 a month in winter time. So there's massive variations seasonally now. That's new. There's also massive variations in time of use. So 90% of Santa Barbara's electricity bill is tied to the time at which electricity is consumed for desalination. It's charged in that 4 to 9 p.m. period window. And so, or I should say, it's tied to time of use, but 30 to 50% of that electricity bill is charged between 4 p.m. and 9 p.m. So this creates clear energy arbitrage opportunities where shifting the load of the plant would not only benefit the electric power grid by reducing congestion on the grid and especially challenges with generation at that time of day, but it would also save the desalination plant a tremendous amount of money when it comes to delivering water. We've actually done a lot of work with this plant to better understand just how much you could potentially save, both under scenarios in which you maintained the full capacity of the plant, as well as scenarios in which you were to curtail that capacity, particularly in years in which you don't need all of that desalinated water because you're spilling water over the top of your reservoir anyway. And I'll say that we've structured this optimization problem, it's a dynamic optimization problem, to minimize the monthly electricity costs subject to the prevailing electricity tariff structure, the existence of demand response calls. So those are not standard electricity tariffs, but those are emergency situations in which there's a risk of a brownout if we don't shed load. And there's an opportunity for desalination plants to derive value from that kind of participation in those emergency demand response programs. The dynamics of the facility, things like how quickly can it start up or shut down, and monthly water production requirements that the city needs to make sure that the water supply for Santa Barbara is secure. So we've done this and we've structured this as a multi-period optimization problem. We have a digital representation of the plant, and at the same time we're calibrating that very actively to things like what's your water recovery rate in the system, how well is their pretreatment system working, and what are the rates of the prevailing tariff rates for the electricity sector. I'll also say what you can see in the top plot is that there's a period of restabilization, particularly at the Santa Barbara plant, where it takes a long time to remineralize the water and get that line-based remineralization system back up and running. So we've also accounted for things like the lag between restarting the plant and when you can actually start to deliver water back into that system. I don't expect you to look at the actual dynamics, but we've provided a script to Santa Barbara this past month between July 7th and August 7th, asking them to turn off and restart their plant on a sort of dynamic basis. And the result was that they were able to save 18% on their electricity bill in the month of July/August, which is an incredibly significant savings for the city when it comes to exploring new pathways to enhance the affordability of those desalination systems. I really think that this is the future, kind of moving away from kind of closed loop facility management for both enhanced efficiency, again, which Zahi will talk about tomorrow, but also for facile and enhanced infrastructure coordination. So it's really about how do we move to a regime in which we are actively representing and modeling a plant, simulating and forecasting its performance, intervening, and then collecting data, cleaning that data, because it's never clean, and assimilating that data to inform what our next decision steps should be. I'm actually going to skip the next couple of slides in the interest of time and turn instead to the foundational gaps that I see or needs that I see in digital twin development. The National Academies actually came out with a report at the end of last year trying to put a kind of definition on digital twins. It's kind of everybody's most favorite and least favorite catchphrase today. And I thought it would be helpful to share what the broader scientific community sees as the frontier in digital twin development and kind of the raison d'etre for calling it a digital twin instead of just a model. right? The difference between a digital twin and a model is that a digital twin is designed to be a fit-for-purpose and evolving virtual representation of a complex system with bidirectional feedback. So the physical counterpart is providing data to the virtual representation, and the virtual representation is actively contributing or determining control and decision-making in that plant. Information could flow through a human. So the digital system could make recommendations to operators, like we did, to turn off and turn on the plant, or it could be automated. It could directly start up and shut down the desalination plant to facilitate its sort of maybe faster response time or management of many, many different components of the plant in a way that a single operator simply couldn't do. You can't have an operator, for instance, fluctuating the blending rates of fossil natural gas and biogas at a wastewater facility on a minute-by-minute basis, but you can certainly do that with a control valve and a good digital automation system. So this is not my definition of a digital twin, but I think it is the definition of it's a consensus study by a group of scientists and engineers that do this for a living rather than do water for a living. And I think it's useful for our community to read it. It's an excellent report. It does a lot of deep thinking into digital twinning in the biomedical space, in the robotic space. It doesn't directly touch on water, but I think that there's a genuine opportunity for our community to think through what those research gaps are in digital twinning that translate directly into the water space. So I've made a first attempt at it here, but I look forward to rich scientific discussion about that need and opportunity in the coming breaks. On the fundamental science side, I think that there's a lot of challenge in bridging time and length scales in the water space, in integrating very diverse multimodal data into these digital representations, in thinking about ways to categorize and make sense of all of the data that comes out of our plants. That's actually a real challenge. We don't use most of it today anyway. To figure out how to represent systems when we don't have perfect visibility into plant operation. To think about where uncertainty or even error in our measurement systems can lead to uncertainty in model recommendations and can lead to errors in recommendations that might occur, and figuring out how to prove the safety of those recommendations and the security of the back-end systems that are providing signals to plants, because this is critical infrastructure that is supplying people with water that they need to know is safe. There's also, I think, some scientific challenges in terms of technology translation. So how exactly do you represent a plant is a bit more of a practical question, but it's really important not to overrepresent the plant or underrepresent the plant when building a digital twin. You need to have a digital twin that is itself fit for purpose, right? That is going to require that we balance fidelity of the models with scalability of those models, but also that we understand which of those variables we can observe, because a lot of things that we put in traditional modeling efforts to represent facilities are not actually directly observable over the time scales that are necessary for control. So we rely on proxies. And fundamentally, we need to demonstrate that the digital twins we build are going to work and are going to provide value. It's kind of easy when you're dealing with the kind of coordination with an energy system. You have huge arbitrage opportunities, and you can readily derive financial value. Moving in a direction where you're not just looking at financial value, but you're also looking at water quality or enhanced sustainability of these efforts is going to require making really concrete case about the value that these digital twins can bring. And finally, I think it's important that we think first and foremost about who's going to use these twins. We think about the operators and the barriers to adoption and implementation of a more digitized water system. Data access and data security are very, very important and certainly top of mind for the water treatment system operators that I work with. How do you visualize this data? How do we work this into the existing workflows of operators at plants? How do you include those operators in making decisions? They have lots of heuristic experience in the plant. They're amazing resources for information. How do you include them and elevate them in that decision-making process? How do you figure out what instead is automatable, doesn't require their active intervention? And how do you continuously verify and validate that the recommendations that we're providing to them are accurate and they can trust? Finally, it's going to really require us to change how we train our students and our workforce to actually be able to understand and use these types of models. And it's going to require some massive changes, or it's going to force some changes in the liability landscape. I think one of the biggest barriers to adoption is that current operators can lose their licenses if something goes wrong, right? They are personally liable for failures at plants. And we need to better understand how liability shifts in a legal landscape in order to encourage or promote their willingness to accept these recommendations. I will also just say I think that the existence of digital twins in the commercial space today tends to address one of the three questions that those digital twins could address. So there is a very robust innovation ecosystem around digital operation of plants in the water space today. But those, well, I would say most of those companies are focused on how you should design the system and operate it given current conditions. So they're trying to do optimization of design, operation, and maintenance. They're trying to manage variance, they're trying to detect failure and deviation, and they're trying to assign faults or diagnose faults. And that's super valuable, right? But it kind of leaves on the table two other classes of questions that one could ask with these same digital representations. One is, what will happen if the system is perturbed? What can we use these digital representations to ask questions about how to better respond to catastrophic events, for instance, or what's the benefit of system interventions and modifications? So more on the design side and the response side. And there's also a set of questions that I think is particularly relevant to our community of researchers who are envisioning the next set of water treatment solutions to help us ask what-if questions. So what if different options existed? We can start to value additional information that's collected at the plant, or better science behind sensing systems. We can start to estimate the performance or impacts of new technologies in the context of actual operating treatment plants. And fundamentally, we can better establish technical targets for research and development and valuing innovation. And so I want to close this talk by really asking the question, how much R&D can our community do in silico going forward? How much can we rely on digital twins and these very detailed representations of plants to better understand where our efforts in the laboratory will have real impact? This is a question near and dear to my heart as the research director of NAUI and kind of the steward of federal funds dedicated to R&D innovation. And I'm always trying to ask the question, to what extent can a project or a proposal actually mitigate not just a specific challenge at a specific plant, but the broader system water costs of water stress, right? So let's take a proposal on the development of a new higher pressure membrane, maybe the one that Shihong is going to share with us in the next session. we want to ask questions about what's the value of that new membrane in the context of a variety of different treatment systems. We want to understand how Shihang's or anyone else's new membrane material is going to increase the cost of those membranes, but also how it how its performance is going to change, and then how the combination of cost and performance are going to change the cost of, for instance, desalinating water using LSRO, okay? That sounds easy. In fact, it's really, really hard, right? If you're going to define that decision space, how improvements in cost or performance are going to change the overall cost of producing water, you need to look at somewhere between 10 to the 2 and 10 to the 5 interacting variables in a treatment train, and you need to characterize that over what's effectively an infinite number of possible water quality solutions, right? We can't do that in the laboratory. You can't pilot that, and so we really need to rely on models to help us, go so far as to say digital twins, to help us really fundamentally understand where there's value in innovation at the component level. The same applies at the treatment train level. So we can think about, for instance, LSRO replacing mechanical vapor recompression as a solution. There's going to be big changes in the effect on capital costs of that system and operating costs of that system. And understanding how those changes in capital and operating costs translate to overall costs is actually also non-trivial and fairly complicated. And it's not just CapEx and OpEx ratios, it's what's the effect of that transition on economies of scale, on reliability, on all these other things that ultimately go into determining whether we use a technology to secure water supply systems, and how all of those change the cost of securing water supply systems in that context. Okay, so at this point, you're all ready to walk out the door. You're like, I don't know, I don't care, I just want to work on my better sorbent, right? Of course, not every laboratory scientist can do this, right? And so one of the things that NAUI has really prioritized is delivering computational tools to the water community to help align innovation priorities. We've pulled on the water technology community's expertise in process systems optimization and the water resources community's expertise in portfolio optimization and capacity expansion models to try to help create a ecosystem where we can help really inform and align innovation investments for a water innovation community. I'm not going to go into tremendous detail on those tools. The US researchers that are already in NAUI have seen way too many presentations that I've given on WaterTap or this water techno-economic assessment platform that NAUI's invested many millions of dollars in developing. But what I want to go through is, more importantly for the Israeli counterparts, what WaterTap is and how we can then use WaterTap to inform a second set of tools that NAUI will be developing in its 5-year renewal process around informing and planning adaptation of U.S. water supply systems using those non-traditional waters, using non-traditional waters, and then those models ultimately informing which water treatment sources, or I should say which non-traditional sources we choose to focus on as a research community. So very briefly, WaterTap is an advanced process systems engineering platform for helping us to both value and prioritize innovation. We have a series, or a model library of unified physics-based devices that you can assemble into a treatment train. That optimizing environment or optimization environment helps us to rigorously identify process designs and operating conditions with the lowest levelized cost of water. And I will simply say that we have very frequent releases. And so if you're interested, I'm happy to share more details. ultimately, WaterTap is really valuable in supporting quantitative innovation analysis, helping us estimate the performance and costs of emerging technologies before we invest a lot of effort in their development, benchmarking innovation targets to a set of existing technologies. So will that new technology actually displace technologies that are already on the market, and helps us to de-risk innovation trajectories and prioritize focusing on cost reductions of components versus improving the performance of those components. So for instance, when we were starting out now, we focused really heavily on how to lower the cost of inland brackish water concentrate management. We looked at a range of proposed and emerging technologies in that space, tried to understand which technology was cost optimal and how much its sort of lowest cost implementation would be, and then what would be the value of new membrane innovation in that space. We found, for instance, that if you could create a high-pressure reverse osmosis membrane that went to 300 bar and was tolerant of high salinities, that you could displace some of those technologies, and so it wasn't worth focusing on them. Again, while WaterTap focuses on the value of individual component innovation, we're really interested in also understanding how the costs of individual water supplies and the attributes of those treatment systems for purifying them can help reduce the cost of supplying a city with water. In this case, Santa Barbara. This is the same model I shared with you earlier, but instead of varying hydrology, we've varied things like technology attributes and policy attributes in that system to estimate the marginal value of technology innovation and policy change. And so we can think about innovation is happening in a couple of different areas. One is volume. You either conserve more water or you store more water. The other is cost. What's the ratio of the capital expense to the operating expense? What's the total cost of delivering water from that non-traditional water source? And then time. How quickly can you deploy that technology, and how long does that technology last? And so I don't want to go into tremendous detail here, but one of the things that these models have uncovered to date and will continue to help us better understand is that water innovation costs space. So we've seen again, at least in the Santa Barbara model that we've developed, that these high capital or CapEx technologies or low operating cost technologies really motivate steady production. That's kind of how we've designed and optimized our seawater desalination plants today. But we've also limited interactions with deployment time. In contrast, a low CapEx facility encourages more dynamic drought response, and you see massive cost reductions, 21% reduction in the cost of providing water to Santa Barbara if you can reduce the deployment time by 30% and leverage kind of more small-scale, dynamic, lower CapEx, higher OpEx infrastructure solutions. Okay, so I'm going to just close here and say that it's really, I think, there's an opportunity over the next several days to think about how our R&D efforts can stretch infrastructure dollars by complementing existing centralized infrastructure solutions with versatile, distributed, inclusive, and digitized solutions. We have a challenge of increasing the adaptive capacity of our infrastructure to help respond to climate variability, and I think there's a lot of research opportunity in that space. And I would just encourage us more generally to look for places where technology innovation can unlock big changes in how systems are operated and managed. And with that, I'll close.
Have 15 minutes for questions, so please ask your questions to Meagan if you have them.
Sure.
Big picture question for you.
Please.
Oh, yes. Okay. I've got to get used to this. I feel like I'm at the UN.
big picture question for you. You know, when I spent earlier in my career in California, I thought it was complex with water districts, counties versus state versus city issues of being on the same page for water use management and infrastructure expenditures. I now, by contrast, living in Pennsylvania, feel like that was an incredibly well-organized, collaborative ecosystem by contrast to what I'm seeing where I am now. And it's particularly difficult because, you know, we've got boroughs and townships and counties and states and privately run water companies and energy companies that have very different operational structures, stakeholders, and so on. And this sounds like such an exciting way to make good decisions, but we are still working within the constraints of humanity and policy and politics. So could you comment on how you anticipate this translating into bigger decision making? It's not that I'm saying these different bodies don't want to collaborate and don't want to apply what you were demonstrating so well, but just that piece feels like such a massive gap. And maybe we'll get back to this tomorrow afternoon when we start talking about the bigger social structures, but maybe we can bookend it when they think about it. It was, what can we do as a community of scholars to actually make sure that translation happens, because otherwise this work is for naught?
Yeah, it's a great question, and I actually will respond to it with a little bit of a story. Jared Cohen, who just passed away earlier this year, when he moved to Pittsburgh, he couldn't believe that there were some 57 odd, I'm going to get the number wrong, so I apologize, Jerry, different wastewater entities in the metro area. And he looked at it and was just like, if there's anything I can do to help coordinate them, just get them talking and aligned in some of the challenges in responding to water quality, I will have made a tremendous impact. I think he went to the grave feeling like he failed on that, right? Like that the incentive structure around alignment and coordination was not in place. And so, I say that as a realist, understanding that there's lots of incentive structures for local control, but that the benefits, or I should say the consequences of local control, are significant, right? You're not thinking, you don't have control over what's coming from upstream, and the people downstream of you are rather at your mercy. That's a place where there's a clear market failure, policy failure and market failure that needs to be addressed at a higher level. So in the same way that we're dependent on global interventions and cooperation to address a global pollutant like greenhouse gases, we need state-level interventions or maybe watershed-level policies to incentivize the cooperation of these different regional entities. I think that that's easier said than done, right? Which policies do you implement and how do you pass that politically is non-trivial. But our hope is that in revealing and making quantitative the benefits of coordination, that you at least set the groundwork for informing which policies make sense and motivating action on behalf of legislation, or legislators and the executive branch. I think that not making the benefits quantitative and also not finding ways to compensate the local communities that might experience more cost as a result means that you're always going to have institutional barriers to coordination and very little incentive to play in that game. Yeah.
Thank you.
Faye?
Okay, yeah. So Meagan, great presentation. My question is about the implementation of digital twins. For example, is there a survey to the water industry to see if they are willing to make this change? What will be the impact of adopting these digital twins on their even daily job, their liabilities, and then how do they meet all the regulatory requirements? For example, if right now for existing desal plants, they may have 16 operators. Right now, if they reduce to 4 because they have all these digital twins, what will be the impact on their job?
Yeah. So I don't know of any industry surveys in terms of digital twin adoption. I did lay out a set of questions I think that are important for us to address as a research community. There's also several small companies and large consulting engineering firms that are pushing digital twin-based solutions, and I'm sure have done those surveys. I'm not deeply aware of them, to be honest. I think that I see the use of models for adaptive control of plants and of broader systems not as replacing human expertise, but really as augmenting their expertise. We, in the water industry, are actually very short-staffed. I sit on the Palo Alto Utilities Commission, and all I hear about is how you can't hire anybody to operate your wastewater treatment plant. Right? And so it's not just a matter of, yes, we need digital solutions to help the workforce operate more efficiently, potentially with fewer hands if we can't fill those positions. But I think more fundamentally, what these models are helping us to do is operate in a different way, right? It's not just continuing to operate the way we've operated before, it's operating dynamically, doing new things with the infrastructure, like delivering energy services back to the grid, integrating the ammonia production, or thinking about the seasonal impacts of nitrogen discharge, and ramping up nitrogen removal when it's summertime and there's a risk of an algal bloom, right? So really being much more dynamic in that plant operation. You can't expect an operator to be able to do that without significant support and help making sense of very, very diverse sets of data streams. And I don't want to say data streams as like, ones and zeros coming in. It's things like, what do I think the temperature is going to be over the next month? Because that also is going to affect the rate of algal growth in the Bay Area, right? Yeah. Moshe?
I go back to Sharon's question. I go back to Sharon's questions on how to implement actually those exciting conclusions and taking into action or enforcing policies. Is there any, I would say, effort to gap between what you're presenting and those high-level politicians? Is there any effort in a source from NAUI or from other locations?
Yeah. Within NAUI, we'll be funding 3 regional water system studies, so efforts to implement this with practitioners to inform how, when, and where they decide to deploy non-traditional water sources, desalination and water reuse primarily, to augment and secure their water supply systems. Mm-hmm. And so we want to kind of ground these tools in practical application over the coming 5 years, understand how they work and where they fail, and try to make them better. All of the work that I've done to date has been in very close collaboration with Santa Barbara, but Santa Barbara is a very unique place, right? It has lots of money. It already has a desal plant. They're incredibly cooperative and wonderful to work with, and smart, well-educated operators, right? They're sophisticated, and they care about climate. Mm-hmm. And so it's a great first case study, but it's by no means adequate to say that these tools will translate to the rest of the country. We need to pilot them in other parts of the country and in other settings that are not in the US ultimately, to understand how they translate and how they need to be adapted to work in alternative contexts.
Okay.
David?
Yeah, so following up on those two questions about implementation, I'm curious for your thoughts about alternative business models for making this happen. So you've posited one where it's a utility being advised on infrastructure investments, but can you imagine things like a business model where someone comes in and sells some sort of insurance against drought and they take the risk, or where they get a premium based upon their results? And does that make sense not only in the US but beyond the US to places that are maybe a little less regulated?
Yeah. I think you make a very good point that there are many ways to engage and quite frankly, monetize some of these results. I think that oftentimes your profit, well, I will say, in places like California, where the profit on water is very strictly regulated down to zero, the business model around better plant operation is going to most effectively be run through those plants, right? But there are many other business models where you find the intersection of water systems and other sectors. And I think building business models that leverage the value that water systems are providing to those other sectors can be very different. So in the electricity space, for instance, like there are many different business models around providing demand response bidding tools to plants, or actually just taking liability for the plant actually delivering on that load shedding. There's an EBSCO model, there's a virtual power plant model, there's like many, many different finance models that have been used and pioneered, quite frankly, in the energy storage space that I think we could translate into the water space. But it doesn't stop with energy. I think we think about that in terms of like critical minerals or nitrogen recovery, or where does water interface with these other infrastructure sectors? And we have to really better understand the business models in those other infrastructure sectors if we're going to maximize our value in the water space. I don't think it happens. There's not big bucks to be made in just serving the municipal water sector independently. Although it's an important space to play in. I just think consulting engineering firms have it pretty locked up, to be frank. Meagan. The operator of the audience.
You got me thinking about the possible role for, I think it would be an excellent role for academic researchers between utilities and the software and startup companies that are like jamming this stuff down our throats a little bit with the digital. Because I think we have 3 projects right now at Orange County Water District where we've essentially agreed, we've been pitched on a digital solution by a for-profit company and agreed to go forward with like a pilot. But to me, I feel like what's missing is the academic contributor, because I see academics as the independent third party who also have the bird's eye view and big picture and aspirational thinking about what it all means. We have one project where a company, claims that they can help us manage endangered species and the dam watershed through artificial intelligence and digital twinning of a whole watershed. And I'm like, come on, yeah, right, what do you think about that as far as, because I feel like this stuff's going to happen whether you're there or not doing it, right? There's recognition of the need for more digitalization in the water sector. It's very exciting. AI is like the carrot dangling, and I think maybe we don't always achieve that anytime soon, but digitalization happens along the way to that, which I think is a good thing. So I guess in terms of making an impact, I just wonder if, as a strategy, could university research groups kind of find these cases, because I think it's already happening, and play a role to design a research project on top of the collaborations that are already happening between technology providers and utilities that are trying to figure this out as a pair, but I feel like that third role is needed, if that makes sense.
Yeah. NAUI is certainly aimed to pair academic researchers with industry, startups as well as utilities, and often also tap the national lab resources to help advance some of these tools. I think we've done so to some success, but not complete success. And I think that's for two reasons. The first is that an industry provider in this space today is often a very small startup, and engaging an academic is expensive, right? We want to pay our graduate students $120,000 a year when you account for tuition and everything else, and so that creates some friction in the system.
Right.
I do think that there's a lot of value, though, as an academic community in finding ways to work directly at plants. And if I had to say anything, it's that, it's wonderful to do work in our laboratories, but when we can go work at places like Orange County, we ask better questions. And I think we can also, as you said, help critically evaluate the range of possible solutions from a bit more of an objective third-party stance that's required when you're going to actually go ahead and publish it. It's not, we're trying to build that innovation ecosystem within NAUI. I think there's always room for improvement. And if you have suggestions of how we can do that, maybe that's a bit more of like a seed fund or auxiliary funding to help get that sort of audit function implemented. There's value.
Maybe the old-fashioned way of academic leads grant writing, proposal writing, but since the utilities are already paying money to the startup company for the project, maybe that's like the in-kind to then get supplementary funding or something. Yeah.
Great.
Thank you. That concludes our Q&A, and let's yet again thank Meagan for her wonderful talk.